shear strain, then naturally we do expect the dirac cones to move away from the mirror axes in such a fashion. And so this is a way in which we can parameterize different kinds of strain that we can apply to this system and hence alter this. And as Vidya pointed out, that the movement of these dirac cones is similar to graphene. However, because of the crystal symmetry in these materials that is different from graphene, in graphene there is only one way in which strain can rotate these dirac cones, whereas here we have three independent ways in which we can manipulate the dirac cones in the material. This symmetry analysis was supported by ab initio calculations, in which here they did calculate how different types of strain will alter and change can cause firstly a phase transition into the topological phase, and then subsequently push away the dirac cones away from the zone boundary. So we see here with three different materials that at a certain onset of strain, then we start to see the dirac cones appearing. This characterizes how far away they are, and they do move away. So this is consistent with altimetry analysis. And because of the nice linearity of the dirac fermions, we can make this identification of strain, of the effects of strain with a gauge field. Whereas in the case of non-relativistic fermions, there would also be additional terms of k dot a, and so the identification is not as smooth or straightforward in that case. So here is where we see that the lattice symmetries then give rise to different number of independent coupling constants for the strain, such that this allows us to write down for a particular valley. For a particular value, we can write down the effects of the vector potential, and it's given by the strain tensor and the coupling constant. So all of that was for strain generically, and now we can look at what happens in particular. What is the profile of the strain as we do get in these bilayer systems? Again, we had seen from Vidya's very nice animation how the difference in the lattice constant between these two materials gives rise to causes the buildup of strain, and this strain is then can relax through the formation of dislocations, so edge dislocations, where we should imagine a whole row of atoms that are now missing running through the system. And these rows of dislocations occur at periodic intervals, as can be seen from this TEM image, which is now seen from the top, in which there's a superlattice of dislocations. And so you can see that one of these blocks is probably on the order of 10 nanometers, so that's about 10 unit cells in this. And you can see that this is a really nice, regular array of dislocations, which is pretty cool because often we think of dislocations as being a large uncontrolled strain to the system that it's going to be very difficult to predict the results of. And in this case, because it's so nicely organized instead, that it does alter the electronic properties in a way that we can model. And you can see that these dislocations occur in both axes, in both directions along the crystal axis. So having said that, we can go ahead and model this, and we can consult classical strain theory to give us what is the strain profile from a single dislocation, and sum them up because they occur in a regularly spaced distance apart, to obtain the total strain profile. And this is along one mirror axis, and then of course we have similar behavior coming from the other mirror axis. And again here we can, since we know the material parameters such as the Poisson's ratio, the lattice constant, etc., then we can actually estimate what kind of strain we expect here. And we can put this into our equation, since we have both the coupling, both the degree to which strain couples as a gauge field and the strain field itself, and we can take the curl to then obtain a resulting magnetic field. And so, looking at the numbers that we have, maximum fields in the order of a couple hundred Tesla. And again, because we have to take the cone here, we do need a spatially varying strain in order to produce a non-zero field. And so this comes out very naturally from the fact that we have this periodically varying strain profile from the dislocation. And this gives rise to this periodically alternating field that averages to zero, that produces a positive field and negative field. So just to contrast this with, our other favorite Dirac system, graphene, in which they also have seen pseudomagnetic fields and resulting Landau levels, as you can see from this SPF spectra. Some differences here is that in here, the nanobubbles of the strained nanobubbles occur in localized regions, so individual nanobubbles. And instead, in contrast, our system, because the strain is produced by this dislocation array that actually covers, as we saw, macroscopic regions, it covers the entire sample in a very regular manner. So it can alter the electronic properties in a global fashion, and not just in a localized fashion here. And this was something and this resulting periodic field that we get that alternates throughout the whole sample, actually, we realized that it's actually much more realistic to have a periodic field like this instead of what one might imagine as, being the first field that one thinks of would be a uniform magnetic field. But a uniform magnetic field would actually require a diverging gauge potential, and this would imply a strain field that diverges at the boundary, which is clearly unrealistic to expect in a real system. So this is nice that our system, allows all of these nice properties. And so, having said that, we can then go ahead and look at what the resulting electronic properties of the system are. No surprise, we get Landau levels, and then we can then look at whether some of the consequences, what some of the properties of this are. So, what would we expect heuristically? When the dislocation array varies on scales that are larger than the metric length, then we would still expect the formation of local Landau levels. And since this is true in our case, since from our estimates we do get a fairly large magnetic field, then we can still use this local Landau level approximation, in which now here we will expect for the energy level spacing to depend on a local field strength. So since our field is varying, we also get an energy level that's varying. And the nice thing about Dirac fermions, as Vidya pointed out also, is that the zero Landau level is always at zero energy, regardless of the field strength. So then even as our energy level spacing varies, however, we still will have always extensive, we will always will have states at zero energy, and this gives rise to an extensive degeneracy of states at zero energy. And we can put this, we can then calculate this by adding a periodic field into a Dirac Hamiltonian, and then a sinusoidal field. And here we do see, as we expect, absolutely that